We will begin by proving the Simplicial approximation theorem. We need to make the following observations. Throughout all simplicial complexes, will be finite at delta n containing n be a simplex and let v be a vertex of delta n. So we define star of v in delta n to be those x such that when we write x as summation ai vi, so let v0 up to vn be the vertices of delta n. Then any point x can be written uniquely as a non-negative linear combination of the vi's, and we want a0 to be strictly greater than 0. And define star of v to be the union over all simplexes which contain the vertex v, star of v comma delta n. Each star of v is an open subset of L. So for example, if L is this simplicial complex and V is this vertex, then star of V is this. The second observation we want to make is V0 up to VR are vertices of a simplex if and only if intersection of star of Vi is not empty. One direction is obvious. If the Vi's are vertices of a simplex, then the intersection of their stars is not empty. To prove the other direction, we have to use the fact that two simplexes can intersect only along a common face. Since intersection of star Vi is not empty, So this implies intersection of each of these. This is equal to union Vi in some simplex delta alpha I of intersection is non-empty. So this implies there are simplexes delta alpha I containing Vi such that intersection star of Vi comma delta alpha I is non-empty. So in particular this implies that the intersection of the delta alpha i's is non-empty. Thus the intersection is going to be a face. So it's going to be some simplex delta gamma. And since intersection of star Vi comma delta alpha I is contained in intersection of delta alpha I, this is equal to delta gamma. So this implies that star of Vi comma delta alpha I intersected delta gamma is non-empty. This implies Vi is a vertex of delta gamma. Thus, V1 to Vr are vertices of delta gamma. So this proves the other direction. If Q, the third observation is in the intersection of star of Vi's, then there is a simplex which contains Q V1 to Vr. So as before, there are simplexes delta alpha I containing Vi such that Q belongs to intersection star of Vi comma delta alpha I, which is contained in intersection delta alpha I. So let delta gamma be intersection of delta alpha I. Then, as before, Vi are vertices of delta gamma and Q belongs to delta gamma. Given a simplicial complex, K Let STK denote the barycentric subdivision of K. So we leave it to the reader to define the barycentric subdivision. So we just give one example. If K is equal to as before, so then the barycentric subdivision is let K be a finite simplicial complex, then we can put a metric on K on the geometric realization. So let diameter of K be equal to the maximum over all vertices, the diameter of star of V. Then it is clear that the diameter of the nth subdivision of K tends to 0 as n tends to infinity. So now we are ready to prove the simplicial approximation theorem. Let K and L be simplicial complexes. Says that K is finite. Let F from the geometric realizations be a continuous map. Then there is an n sufficiently large and a simplicial map G from the nth subdivision of K to L such that G is homotopy to F. So proof. We have an open cover thus we get an open cover of K let K prime denote the nth barycentric subdivision of K. And if n is very, very large, then since mod K is compact, we get that for each vertex W in K prime, we have the star in K prime of W is contained in F inverse star of V for some V in which is a vertex in L0. So this is a simple application of the Lebesgue number lemma. And observation 5. So we define G of W to be equal to V. So to show that G can be extended to a simplicial map, it suffices to show that if W0 through WR are vertices of some simplex in K prime, then GW0 through GWR are vertices of a simplex in L. But note that the set F of intersection star in K prime Wi is non-empty, this is in star in L. So now using observation 2, we get that G of W0 up to G of WR are vertices of a simplex in L. Thus, G defines a simplicial map So, to show that G is homotopic to F, it suffices to show that for each x mod k prime, there is a simplex delta R in L such that f of x and g of x are in delta R. Then the straight line homotopy df plus 1 minus t times g defines a homotopy between g and f. So for a simplex, delta R in K prime define interior of delta R to be equal to delta R minus the boundary of delta R. So when R is equal to 0, boundary of delta R is empty. So suppose x belongs to interior of delta R and let W0 up to WR be the vertices of delta R. Then x belongs to the intersection of star wi's. This implies f of x belongs to f. So by observation 3, there is a simplex L which contains f of x, g of W0, g of WR. So since x belongs to intersection star WI, this implies that well, since x belongs to interior of delta R, this implies that x is equal to summation I equal to 0 to R AI WI, where all the AI's are positive. So this implies that g of x is equal to g of WI. So this implies there is a simplex in L which contains f of x and g of x. So this completes the proof of the theorem. So next, we have the following lemma. Let K be a finite simplicial complex let F from mod K to mod K be a continuous map which has no fixed points. Then there is an n sufficiently large such that for each vertex P in the nth subdivision of K, let's call this K prime, we have f of star in K prime of E intersected star in K prime of E is empty. Proof. So, since K is compact Rostov, as before we put a metric on mod K. So there is epsilon positive such that for all x in mod K, the distance between x and f of x is greater than or equal to epsilon. So after choosing n sufficiently large, we may assume that diameter of star K prime P is less than or equal to epsilon by 2. If these two sets intersect, then there is an x in star K prime V such that f of x is also in star K prime P. But this is a contradiction. Since epsilon so this proves the lemma. So if so thus if f from mod K to mod K has no fixed points, then After replacing k by a high enough subdivision, we may assume that f satisfies this condition. So, using the Simplicial approximation theorem, there is M sufficiently large and G a simplicial map. So let's call this L such that G is homotropic to F. Recall that from the definition of G, we have that for each vertex in L, f of the star of V is contained in star in K of G of V. So suppose delta K alpha is a K simplex in K. So let us assume that in L, which is obtained by subdividing K, delta K alpha gets subdivided as a union of some K simplexes delta K beta. So let us assume that G of delta K beta is a K simplex. That is, it has dimension K. Or equivalently, G takes all the vertices to different vertices. Thus, G of delta K beta is equal to delta K gamma for some K simplex delta K gamma sitting inside K. So we claim that delta K gamma is not equal to delta K alpha. So if not, assume delta K gamma is equal to delta K alpha. Let W0 up to WR be the vertices, not WK. Be the vertices of delta K beta. By the definition, of G, we have that for each I, f of star of Wi is contained in star of G of Wi. So this implies f of intersection star of Wi is contained in intersection star of GWI. So since the interior of delta k beta is contained in intersection of star of Wi's, we call the interior is this implies that f of is contained in this contained in for all I. So since delta k beta appears in delta k alpha appears in the barycentric subdivision of delta k alpha, it follows that for every vertex v in delta k alpha, we have interior of delta k beta is contained in star k of v. Since v is equal to g of wi for some I, as we are assuming delta k gamma is equal to delta k alpha, we get that f of star of k v intersected with star k of v is non-empty. So that follows because of this equation. So this is a contradiction. So this proves the claim. So let's put the claim aside for a minute. So a simplicial complex K can be given a CW structure in an obvious way. So the natural inclusion mod K mod of the subdivision, and its subdivision is a CW map. So both these assertions are clear. And similarly, a simplicial map induces a CW map on the obvious CW structures. Thus, we have maps of CW complexes which induces maps of complexes So let us try to understand what these maps are. We call that CWNX, well, mod K, this is the nth homology of the n skeleton mod the n minus 1 skeleton. This free abelian group on n simplexes. The map I lower star is described as follows. Suppose delta n alpha gets subdivided as a union of delta n betas. So recall that L is the mth subdivision of K. Then I lower star of En alpha. So En alpha is the basis element corresponding to delta n alpha, is, one easily checks, summation En betas. If G of delta and beta has dimension strictly less than n, then g lower star e and beta is equal to 0 as the image of g then lies in the n minus 1 skeleton. If g of delta and beta is an n simplex, then it is delta and gamma for some gamma. So from the preceding discussion, it follows that gamma is not equal to alpha. Thus, it follows that g lower star of I lower star of E and alpha is a sum E and gammas, and E and alpha does not appear. So this shows that when we look at the map, of free abelian groups, this map has trace 0. So this implies summation I equal to 0 to infinity, well, j equal to 0 to infinity minus 1 to the j trace of gj I j is equal to 0. So note that this is a finite sum, since CW dot is a finite complex. Only finitely many terms are not 0. So let's prove a lemma that A dot be a complex of Q vector spaces such that only finitely many ANs are not 0. That H dot from A dot to A dot be a map of complexes. Then summation I equal to 0 to infinity trace of H star from HI to HI is equal to So proof. So this follows easily. Using the short exact sequences. So this will imply the trace of h from an to n is trace of h from bn minus 1 to bn minus 1 plus. So this will imply that trace of h from Zn to Zn is equal to trace of h from Hn to Hn plus. So combining these, the lemma easily follows. So we take an alternating sum. So in view of the lemma, we get that summation j equal to 0 to infinity minus 1 to the j trace of gj ij from the NHCW homology of mod k with q coefficients is equal to 0. But as the CW homology is naturally isomorphic, to singular homology, we have a commutator diagram. Moreover, since f and g are homotopic, this implies that g lower star is equal to f lower star on singular homology. So thus we get that is 0. Thus, we have proved the following theorem due to Lefschetz. Let K be a finite simplicial complex. Suppose f from mod k to mod k is a continuous map such that f has no fixed points. Then the Lefschetz number which is defined to be the Lefschetz number is 0. So, remark, the above says that if the Lefschetz number is non-zero, then f has a fixed point. In fact, in many situations, it can be proved that the number of fixed points is exactly the Lefschetz number. So we will end here.